minus 1. But don't forget, that's impacted by the value of n. So if n is equal to 1, L can be 0 all the way up to 1 minus 1 is 0. Well, that means the only value of L is 0 when n is equal to 1. Does that make sense? It's the value of n that determines how many values of L you should have. And this is the sort of thing you can talk to your grandparents about. I'm sure they'd enjoy it. Or it's great for cocktail parties. Does everyone see? What if n is equal to 4? What are the possible values of L?
0, 1, 2, 3.
That's it. Like taking candy from a baby, right? And for convenience, physicists and chemists have given letter designations for different values of L, and they have similarities as to the shape on 3 dimensions. When L is equal to 0, we say that that is an s orbital. And all s orbitals have about the same shape, but as you go to increasing energy levels, they have larger radius. Okay? The bigger. And it's a region of space electrons occupy. Now, for each value of L, now we have what's called the magnetic quantum number, and m sub L. So for a given value of L, so the magnetic quantum number m sub L can range from minus L dot 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 0 dot 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 up to plus L. Well, if L is equal to 0, there's only one value of m sub L, because minus 0 is the same thing as 0. So there's only one value of m sub L when L is equal to 0. When L is equal to 1, well, now you're going to have 3 values of m sub L. When L is equal to 1, what are the values of m sub L?
Negative 101.
It says negative 101. And again, if you came in late, I printed this out. Did anyone not get one of these? I don't know if I printed enough. I apologize. Hope I did. And so I'm just pointing out what this slide, which is right off the slides, this is right off the PowerPoint. Hey. There you go.
You have them still?
Yeah, I have one. I don't think I printed out enough, but there's a couple people playing hooky, I guess. Either that or they're at home enjoying quantum numbers. All right, so that's the magnetic quantum number. And if this seems odd, you can only, I can't even put into words how horrible the calculations are when you actually have to take a course in this stuff. You're just looking at the pictures. This has been derived using a very complex differential equation. The Schrodinger wave equation. I think I told you, there's a bumper sticker, honk if you pass pecan, and nobody's honking. And that's where you actually do the calculations that you determine this technique and these quantum numbers. And then m sub s, the spin quantum number, fortunately, is kind of easy. It only, regardless of the orbital, m sub s has to do with the 2 spin states of electrons in orbitals. And it's just plus 1/2 and minus 1/2. Electrons have a property called spin. Generally speaking, if 2 electrons occupy the same orbital, they have opposite spin. And the spin state of the electron can be thought of kind of as generating a tiny magnetic field. And so atoms of elements that have odd number of electrons can be separated by the fact that the odd electron has two possible spin states. And then also, generally speaking, if two electrons are in the same orbital, they're going to have opposite spin. Don't forget, at least one quantum number has to be different. So if two electrons, if the first three quantum numbers are the same, well then the fourth one has to be different, the spin. And those would be the two electrons that are occupying the same orbital. Now, this sheet is just right off the slide, but you can kind of see the manifestations of these rules. I mean, when n is 1, there's only one value of L, there's only one value of m sub L, there's only one orbital, and we call it a 1s orbital. We mentioned here that when L is 0, we call that an s orbital in any energy level that has it. And s orbitals are in all the energy levels because it corresponds to L equals 0. So there's an s orbital in the first energy level, another one in the second, another one in the third. But when you get to L equal 1, there's three values of m sub L, and we refer to those orbitals when L is equal to 1, you have three values of m sub L. We call those p orbitals. When L is equal to 2, there's 5 orbitals, 5 values of m sub L. We call those d orbitals, and they actually give the transition metals their properties. And you get the idea. So we use a letter designation, and that's also shown in this sheet. When n is equal to 1, L is equal to 0, m sub L is equal to 0, that is just one orbital, and we call it the 1s orbital. The 1s tells the chemist it's in the first energy level, and that L is equal to 0. The letter S tells the chemist that L is equal to 0. In the second energy level, you've got one orbital where L is equal to 0 and m sub L is equal to 0, and we call that the 2s orbital. In the second energy level where L is equal to 1, now you have three values of m sub L. They all have the same energy. We call those p orbitals. There's three of them. They have the same energy. There's 2px, 2py, 2pz, and so on. And so this kind of spells out, really these orbitals result from these rules for these quantum numbers. Okay? And again, there's a slide. And an orbital really is a solution to the wave equation that gives a probability density where the electron spends over 90% of its time in that specific energy level or region. Now, all s orbitals are intuitive. This is what we might think an orbital looks like if we had no idea. The 1s orbital is the s orbital in the first energy level. The 2s is an s orbital in the second energy level, and so on. And they're all quasi-spherical. And this is kind of what we, if you take a biology class, they try to tell you a little bit about this stuff. And usually they draw circles or something for electron orbitals. But when L is equal to 1, well, the solutions to the wave equation are such for the energy that you don't have an intuitive shaped orbital anymore. And there's a degeneracy of 3. What that means is there's 3 values of m sub L. They all have the same energy. And so here are the 3 2p orbitals. They have nodes. This is the 2px, this is the 2py, this is the 2pz. These p orbitals are perpendicular to one another, and even though you see two spheres, that's one orbital. Okay? And that corresponds to when L is equal to 1, m sub L is equal to 1, or actually m sub L is equal to -1, 0, and +1. And these three p orbitals have the same energy, they're just perpendicular to each other. One thing to keep in the back of your mind, based on these rules of quantum number, you can't have any more than 2 electrons in an orbital. And they have to have opposite spin. Again, they've got to have at least one quantum number is different. So if 2 electrons are in the same orbital, they have the same value of n, L, and m sub L, but at least their m sub s, their spin quantum number is different. That's a Pauli exclusion principle. At least one quantum number has to be different. Okay? Well, it really gets fun when you get up to L equal 2, and these are the 5d orbitals. They start to look like Dunkin' Donuts with dumbbells in them and whatever. These d orbitals, we don't really encounter them until we get to the transition metals on the periodic table. They're in the center of the periodic table. And these d orbitals actually give these metals their properties. When L is equal to 2, as it shows you on your sheet, there's 5 values of m sub L, -2, -1, 0, 1, and 2. So these are 5 degenerate orbitals that have the same energy. And we can and they're designated on your sheet as 3D XY, 3D YZ, and so on. I'm going to kind of skip over this. So again, really what we're trying to say today here is the Pauli exclusion principle. When you're determining the most stable state of electrons in an atom, of an element, no 2 electrons in an atom can have the same 4 quantum numbers. At least one of the numbers has to be different. Okay? So just to read this slide, the Schrodinger wave equation, there's 4 quantum numbers used to describe electron energies in atoms. And the Pauli exclusion principle is stated here. And this is essentially a manifestation of these rules for quantum numbers we've been talking about. It's kind of like a stadium, a football stadium. There's no 2 seats that are exactly the same. There has to be something different about each one. So the values of the quantum numbers, n is really the shell, L can be thought of as the subshell. When you get to m sub L, you get to unique orbitals. And then, of course, an orbital can have no more than 2 electrons. An orbital can be empty. It can have 1 electron, or it can have 2. The way chemists look at it is that an orbital is available even if there's no electron in it, in an atom. Well, based on what we talked about, we can put together the energy of these orbitals in an energy diagram like this. Now, the first element that was studied was hydrogen, and this is a painfully, trust me, painfully simple equation for the energy of the electrons in hydrogen. And it's nowhere near this simple for the other elements. We have a painfully simple equation for the energy of the electrons in hydrogen. This is a Rydberg constant, and then n is just the principal quantum number. If we know what energy level it's in, well, we can easily calculate its energy. This is just for hydrogen. You can't use this equation for the other elements. The reason is because atoms get more complicated when you have, say, two protons in the nucleus and you've got 2 electrons. Then the wave equation, I hate to say this, becomes insolvable. Now, if you can't solve the Schrodinger wave equation for any atom except for hydrogen, what good is it? Well, they use approximation method. And when they use those approximation methods, they still come up with orbitals that are very similar. But this energy diagram is for hydrogen only. Notice that when you get to the second energy level, the 2s orbital and the 2p orbitals have the same energy. That's why we can use this painfully simple equation for the energy of electrons in hydrogen. But when you go to multi-electron atoms, and then you're going to start with helium, and then every other element on the periodic table, that's not quite as pretty. But using these approximation methods, we come up with this kind of arrangement for the energies. And you can see now, when you have more than one electron in an atom, it causes slight differences in the energy of 2s orbitals versus 2p orbitals, difference in energy between 3s and 3p, and it also comes up with a rather bizarre manifestation of 3d orbitals being higher energy than 4s. So they're kind of doing this kind of thing. Now a diagram like this can help us in determining what's called the electron configuration of electrons in atoms. All the electron configuration is determining what orbitals electrons are in their most stable state in an atom. And you use what's called the Aufbau principle from the German building up, and you assign electrons from the lowest energy and you work your way up. So if let's say an atom like lithium has 3 electrons, well, 2 of them are going to be in the 1s orbital. And what can you say about those 2 electrons in the 1s orbital?
They're opposite.
They have opposite spin. And that orbital's full. And then lithium has 1 more electron, so you go to the 2s orbital, and there's an electron there. And that is a rather simple example of electron configuration. They get more complicated. On the back of the sheet I gave you, it shows you electron configurations for elements. And we're going to look at some examples of that. So again, we can use this kind of energy diagram for multi-electron atoms. We don't really need it for hydrogen anyway. Hydrogen only has 1 electron, so in its most stable state, it's in the 1s orbital, end of story. But let's do a few simple electron configurations. And as strange as some of this stuff may seem, simple electron configurations are not bad. We're just going to use this diagram I have up here. These orbitals came from the rules of the quantum numbers, and we have them on an energy diagram here. We know the Pauli exclusion principle is true. No 2 electrons in an atom can have the same 4 quantum numbers. We know the Aufbau principle is true. When we determine the electron configuration, we start at the bottom and work our way up. The simplest element on the periodic table is hydrogen. It has, if it's an atom, it has 1 electron, and it's going to be in the 1s orbital. And so we say the electron configuration for hydrogen is 1s1, easy. What this means is there's 1 electron in the 1s orbital, and you don't really need to think about it all the time, but the 1 means n is equal to 1, and s means L is equal to 0. But you don't have to think about that all the time. The next one is helium. Well, it's got 2 electrons, and we can have up to 2 electrons in an orbital based on the Pauli exclusion principle. But they have to have opposite spin. But in the electron configuration, it doesn't necessarily show that. So we can have electron configuration is 1s2. There's 2 electrons in the 1s orbital, and we just know they have opposite spin. If we're doing it on an energy diagram, here's our 1s orbital. Sometimes the chemists do it like this. They're just emphasizing that the electrons have opposite spin when they write it like this. Okay? What's the next element on your periodic table?
Lithium?
Lithium. It has 3 electrons, so it has 2 electrons in the 1s orbital and 1 electron in the 2s orbital, and we'll put it here. Okay? Now these electron configurations are probably on the sheet I gave you, aren't they? Now, one thing about electron configurations, when you make it, if you have a periodic table and you make it all the way to the right, and you reach the noble gases, you know from what we've talked about, the noble gases are unusually stable, filled shell. So another way we can write helium, kind of silly, but we can just put helium in brackets because it's a noble gas. And another way we can write lithium is helium in brackets and then 2s1. When you have this few electrons, and I got this screwed up on, this is 1s2. Well, let me do that. 1s1, 1s2, 1s2, 2s1. We didn't really save any ink here, but when an atom has 91 electrons, you can save a lot of ink by putting the nearest noble gas symbol first and then show the rest. If you look at the sheet I gave you, let's find atomic number 55 is cesium. Instead of writing all 55 electrons, all you have to put is xenon in brackets and 6s1. Okay? See how we saved a lot of ink. Okay? What's the next element? Of course, is beryllium. It's got 4 electrons. There's 2 in the 1s orbital, they have opposite spin. 2 in the 2s orbital, they have opposite spin. This is 1s2, 2s2, or we could write it helium 2s2. Okay? Now we've filled the 2s orbital, so now we got to go into those 2p orbitals when we get to boron. And so for multi-electron atoms, the 2p orbitals are at a slightly higher energy than the 2s. But that wasn't true for hydrogen, but all the other elements it is. And so we have 2px, 2py, and 2pz. And they all have the same energy, so it doesn't matter which one we put the electron in. So for boron, the 5th electron is here. So for boron, it's 1s2, 2s2, 2p1. And notice that when we write the electron configuration, we don't show all 3 p orbitals. We just say that there's 1 electron in the 2p orbitals somewhere. Or we can write it helium 2s2, 2p1. Again, there's not enough electrons, it's not really saving us any ink to do it that way. Now, 2 rules we mentioned. One was the Pauli exclusion principle, where every electron in an atom has to have a unique set of quantum numbers. We've also mentioned the Aufbau principle, which just means building up, and that's what we're doing now. We're assigning electrons from the lowest energy, working our way up. Another rule involving electron configuration is Hund's rule. This is Hund, not Hunt, so don't blame me. Hund's rule. And this has to do with when you have orbitals of equal energy, like here. Chemists refer to these as degenerate orbitals because they have the same energy. Well, you don't pair electrons in an orbital if there's another orbital available that doesn't have an electron yet. You spread them out. And we'll see that with the next example. After boron, we have good old carbon. And carbon has a total of 6 electrons. 1, 2, 3, 4, 5. Again, we don't pair it here. We pick one of these and spread it out. Don't forget, electrons have negative charges. They repel each other. So they're going to occupy different orbitals before you put 2 in the same orbital. Okay, that's what's called Hund's rule. Okay? Again, that doesn't really show up over here. We have 1s2, 2s2, 2p2. Or helium, 2s2, 2p2. Okay? Now eventually what you'll get all the way across the period to the noble gas, and that's going to be neon. And it has 10, so we'll just skip the neon. It has 1, 2, 3, 4, 5, 6, 7. I spread them out by Hund's rule. 8, 9, 10. And we have another filled level because it's a noble gas. So for neon, 1s2, 2s2, 2p6. These p orbitals are filled, aren't there? There's 3 of them, and you can have 2 electrons in each one. Or you could have helium, 2s2, 2p6, or you could have neon. It's a noble gas. It's filled. Okay? Those are 3 different ways of writing the electron configuration for neon. Now, again, these are just some of the simple examples, and then you got more examples on this sheet. Here, here is the element nitrogen, and it's showing you Hund's rule with the p orbitals. There's 2 electrons in the 1s orbital. They have opposite spin. 2 electrons in the 2s orbital. They have opposite spin. And then there's 3 more electrons. We got to spread them out before we pair them. This is, again, Hund's rule. Okay? This is another energy diagram that's sometimes used for determining electron configurations. You start at the top and you fill the 1s orbital first, then the 2s orbital, then the 2p orbitals, the 3s, the 3p, the 4s. You get the idea. Okay? Don't forget, wherever you have an s orbital, it can have up to 2 electrons. When you have p orbitals, they can have up to 6, and d orbitals can have up to 10. Okay? So here is the electron configuration of hydrogen. There's 1 electron in the 1s orbital. The 1 tells us the principal quantum number is 1. The s tells us the angular momentum quantum number L is equal to 0. And this is the number of electrons in the orbital. Okay? Now, because of the fact that electrons follow Hund's rule, and also the fact that when there's 2 electrons in an orbital, they have opposite spin. This can have magnetic properties, even on elements that we don't think have much in the way of magnetic properties. when you have unpaired electrons where you have two electrons that have the same spin in different p orbitals, for example, it's going to cause a slight magnetic moment to the atoms of that element that we call paramagnetic. On the other hand, when an atom, all orbitals have two electrons of opposite spin, the magnetic fields cancel each other out. And those elements are diamagnetic. Okay. All right, I'm skipping over this problem because we're going to look at some practice problems. This is a pretty good diagram and showing an atom with 8 electrons, what its quantum numbers are. Another thing about the spin quantum number, they have the same energy, so it doesn't really matter if it's plus 1/2 or minus 1/2. But when you have 2 electrons in an orbital, one of them's plus 1/2 and the other one's minus 1/2. This is the handout I gave you. Now looking at the outermost subshells that are filled for different elements. The first 2 groups on the periodic table, group 1A and 2A, the alkali metals and the alkaline earths, the valence electrons for those elements are in the new s orbital. Don't forget, when you go across and then you go to the next period, you're going up an energy level. So in the first 2 groups, a new s orbital is being filled. And just look at the sheet I gave you and find something like, oh, just pick one of the alkaline earths, for example. Well, pick magnesium, atomic number 12. Well, its electron configuration is neon, which is the last noble gas that got filled, and then it's got 2 more electrons in the 3s orbital. Magnesium's right here. So those are the valence electrons. This sheet is showing you for main group elements the valence electrons because all the other electrons are in filled noble gas configuration. Okay? What determines of the orbitals, what determines if you end up with a very stable noble gas is not the d orbitals or the f orbitals, it's the p orbitals. Except for helium, of course, which only has 2 electrons. When you get to neon, argon, krypton, they have filled p orbitals. In the second period, neon has 6 electrons in the 3 2p orbitals. So there's something about the p orbitals that makes, when they're filled, that makes the noble gases so stable. But the d orbitals are important because when we encounter these d orbitals for the first time, and notice the 3d orbitals, we encounter them after the 4s. There's that kind of crooked feature there. These d orbitals are what give these transition metals their properties. What kind of ions they form, what kind of complexes they form, what kinds of ligands interact with them. And then you got the actinides and lanthanides. These are unusual elements where f orbitals are being filled. So this kind of just shows you which orbitals are being filled in the outermost shell for these different groups of elements. People that are good at electron configurations can use the periodic table to figure out electron configurations, but in this course I'm going to keep it easy. I'm either going to let you use a sheet like this or whatever. Try to keep it simple. One thing, when you do, here's palladium, for example, and you can see the importance of using noble gas designations. Which noble gas is filled when you fill the 4p. Well, you have to look at your periodic table, but see how palladium is 46 electrons. So here's its full electron configuration, but if you look at the sheet I gave you, you got krypton and then then you got the 4d10. So these are the outermost electrons, and the rest, all this stuff, is krypton, the noble gas. Okay? Alrighty, now, I gave you some practice problems. Has anyone had a chance to start any of the practice problems yet? Well, these practice problems are similar to problems on the exam. So again, hopefully they help you. I'm going to show you how to set some of these up. As far as the lab this week and next, it's real simple, but I don't know, Cassie, if you, Donnie, if you mind helping me. We just need to see if we have the reagents to do it. But it's just doing some little spot tests that don't take very long. And we're going to spread it out. We're going to do some of it Thursday and some of it a week from Thursday.
Okay.
Don't forget, on Friday, we have the extra credit quiz for the lecture, which is balancing chemical reactions.
Is that Friday or Thursday?
Did I say Friday? I'm
Yeah.
going to. Thursday, don't make a special trip, especially since the college is locked. I meant Thursday. On Thursday, we have the quiz and the lecture that's extra credit, balancing chemical reactions. And then we have a quiz in the lab, which is the gravimetric analysis. I need those for this goofy college assessment thing. You know, it's not in my job description, but I guess I have to do it. And then we'll have a very short lab on Thursday. Today, after we go over some of these practice problems, I want you to go to the computer room for a while. And yeah, so the lab we're doing on Thursday and a week from Thursday is pretty simple. They're little spot tests involving different ionic compounds to see if they react. You only put a few drops of each in a little plastic well, and you just observe it and write down your observations. If you have them, get out your practice problems, and let's go over how to set up a few of these. Has anyone seen Suzanne? All right, practice problem number 1. What is the wavelength of radiation in nanometers that has a frequency of 8.79 times 10 to the 15 reciprocal seconds? And for frequency, sometimes they put cycles per second, and other times they just put 1 over seconds, which is called reciprocal seconds, because the cycle is kind of assumed. So we know that the frequency, this is nu, the Greek letter nu, is 8.79 times 10 to the 15th reciprocal seconds. That means 1 over seconds, or cycles per second. Also, we know c is the speed of light, 2.9979 times 10 to the 8th meters per second. The relationship, the speed of light in meters per second is equal to lambda, the wavelength, in meters per cycle, or just meters, times nu, the frequency, and this is in cycles per second, except again, a lot of times we don't even worry about the cycles. In which case this would be meters and this would be seconds to the minus one. But you do need to be conscientious, even though it's a simple equation, you have to be conscientious of units. So if you rearrange this, of course, lambda is going to equal the speed of light over the frequency. That's what the problem's asking for. And speed of light 2.9979 times 10 to the 8th meters per second divided by the frequency 8.79 times 10 to the 15th reciprocal seconds. This is 1 over seconds, but this is 1 over seconds, so they cancel. And this wavelength will be in meters. But that's not what the problem asks for. It wants the wavelength in nanometers. And so you also, in fact, you can even put it in this calculation if you want. Just do it all in one step. Milli, micro, nano, 1 meter is equal to 10 to the 9th nanometers. And so you multiply this times 10 to the 9th nanometers over 1 meter, and the meters cancel. Okay? Everybody see how to set that one up? When the speed of light was in meters per second, the frequency was in reciprocal seconds, but the problem wants the wavelength in nanometers. So you can do this, your answer will be in meters, and then you need to convert it to nanometers. Okay? Or you can do it in one calculation. Okay? Again, none of this you have to memorize. This equation will be on the formula sheet. 1 meter is equal to 10 to the 9th nanometers. Let's move on to number 2. Everyone see how to set that one up? So it's kind of a simple equation, but you got to be conscious of unit. Number 2, calculate the frequency of visible light that has a wavelength of 686 nanometers. And again, rearranging the same equation. Frequency is going to equal the speed of light divided by the wavelength. So we have 2.9979 times 10 to the 8th meters per second, the speed of light. The wavelength, we have 686 nanometers. And then we can either convert the meters to nanometers up here, or we can convert the nanometers to meters down here. If we do it up here, let's just go ahead and use the factor we had before. 10 to the 9th nanometers over 1 meter will enable us to cancel the meters here. And then the nanometers can cancel. You gotta be conscientious of units. Or if you wanted, you can convert nanometers to meters before you even do the problem. Okay? Everybody see how we set that one up?
So it doesn't matter if it's in meters or nanometers?
No, it does.
Well, either you gotta convert those meters to nanometers, or you gotta convert these nanometers to meters so you can cancel them. Either way. So you can either put this up here, or you can flip it and put it down here. You get the same answer. Okay. All right, number 3 here. We mentioned that electromagnetic radiation includes visible light, radio waves, microwaves, infrared, ultraviolet, gamma rays, X-rays. It's all the same thing. Our eyes can only see a narrow range from 400 to 700 nanometer wavelength of electromagnetic radiation, but we still get to see all the beautiful colors that we see. Well, in this problem, no matter what kind of electromagnetic radiation it is, the smallest particle is called a photon, and it can be thought of as a packet of energy, if you will, in the way that it interacts with matter. It's asking what is the energy in joules of one photon of microwave radiation with a wavelength of 0.179 meters. So that's a pretty big wavelength. It's pretty low energy. It's not as big a wavelength as radio waves that you listen to on your radio. They may be the size of a football field. The longer the wavelength, the lower the energy of the photons. Whereas you have something like gamma radiation, the wavelength's ridiculously small. The frequency is extremely high. So, the energy of a photon, again, is a very simple equation. It's equal to Planck's constant times nu, the frequency, or it's equal to Planck's constant times the speed of light divided by the wavelength. And the problem gives you the wavelength and the speed of light and Planck's constant. So, Planck's constant is 6.626 times 10 to the minus 34 joule seconds times 2.9979 times 10 to the 8th meters per second divided by, conveniently they give you the wavelength in meters so you don't have to worry about changing it. The wavelength's 0.179 meters, and so the meters cancel, the seconds cancel, and the energy of the photon is going to be in joules. Okay? It's the only thing left. Does everybody see how we set that one up? And that one wasn't too bad because we didn't have to convert anything to anything. Let's see here, what do we got next? Now the equation for the energy level of electrons in a hydrogen atom, I think we emphasized, is misleadingly simple. It's only hydrogen that has such a simple equation. All the other elements of the periodic table, they have to use a Schrödinger wave equation to do complex calculations when you have more than 2 electrons in an atom, or 2 or more. But Bohr, the scientist Bohr, it's B-O-H-R, not boring, Bohr, came up with this very simple equation for the energy levels in hydrogen. And it's on problem number 4. Calculate the energy in joules required to excite a hydrogen atom by causing an electronic transition from n equal 1 to n equal 5. Recall that the energy levels of a hydrogen atom are given by the simple formula: the energy of an electron in the nth energy level is the Rydberg constant times minus 1, I should say, minus 2.18 times 10 to the minus 18 joules times 1 over n squared. That's extremely simple equation. And there's more than one way to do a simple problem like this. But one way is just to figure out the energy of the electron at each energy level and subtract them. Okay? Let's think about what's going on here. If you have an electron in an orbital, and we're talking about hydrogen at the moment, and it has other orbitals with other energies. If an electron absorbs a photon of the right energy, and then has an energy exactly equal to this change, it will cause the electron to go to a higher energy level, and we call that an excited state. So if an electron's absorbing electromagnetic radiation and going to a higher level, that's one type of problem. It started here and it ended up here. On the other hand, if an electron's in an excited state to begin with, and it returns to a lower energy level, well, now it's going to give off a photon that's equal to this change in energy. So the first example, it was absorbance of a photon. The second example is it's emitting a photon. In problem number 4, the electron is absorbing a photon. It starts out at n equal 1 and it goes up to n equal 5. Well, the change in energy, which would also happen to equal the energy of the photon, by the way, that caused it, is just going to equal the energy it ended up minus the energy it started out. And so if you calculate each of these, you just subtract. So energy, and when the electron's in the 5th energy level, this is just a negative 2 point, and again, this has to be hydrogen, it can't be one of the other elements for such a simple equation. And of course, it's in the 5th energy level, so we have to multiply that times 1 over 5 squared, don't we? Or 1 over 25. In other words, we just take this divided by 25, right? And then the first energy level is equal to the same negative 1 times the Rydberg constant here. Except it's going to be over 1 divided by 1 squared, which is the same thing as this, isn't it? This is going to be 1. 1 over 1 times this gives you this. Once you know each of these, you subtract E1 from E5 to get the answer. Does everybody see how to do that problem?
Yes.
Okay. Oh, boy. Number 5, now this is one way you can do it, and number 5 we'll look at it, it's a different problem, but there's another equation. Again, it's just based on the same one we just used, but number 5, you have the wavelength of light emitted by a hydrogen atom during a transition of the electron from n equal 5, now this time to n equal 2. So it's excited. Maybe you've got hydrogen in an electron discharge tube, you apply electric current, some of the electrons go to the 5th energy level, and then they drop down to the 2nd one, and they emit a certain wavelength of light when they do that, okay? Another approach, we could obviously determine the energy of electron in the 5th energy level and the energy in the 2nd, and we can subtract, just like we did over here. Or there's another way of doing it, just it combines these two terms, this change in energy, which is the energy of the photon this change in energy is equal to the Rydberg constant times 1 over the initial quantum number squared minus 1 over the final quantum number squared. Here you just do it in one calculation. These got flipped, so you got rid of the negative sign that you saw over here. And this Rydberg constant is the same thing as 2.18 times 10 to the minus 18. It was initially in the 5th energy level. It ended up in the 2nd energy level. Okay? Everybody see how we got this? Now this is the energy of the photon. Okay? Well, that's the energy, but that's not what the problem's asking. Once we have the energy of the photon, what do we have to figure out?
The wavelength.
The wavelength. Well, the energy of a photon is equal to Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. Therefore, the wavelength is going to equal Planck's constant times the speed of light divided by the energy of the photon. And that's what we figured out here above. Don't forget the amount the energy changed when the electron dropped from a higher energy level to a lower one is exactly equal to the energy the photon it gave off. And once you know the energy of the photon, then you can use this equation, Planck's constant times the speed of light divided by the energy of the photon will give you the wavelength. Okay? And I don't know if you want me to insert those values. We have Planck's constant is 6.626 times 10 to the minus 34 joule seconds. Okay. We know the speed of light is 2.9979 times 10 to the 8th meters per second. Okay. And then this is over the energy of the photon that we determined up here. Don't forget that this wavelength is going to be in meters because the speed of light is in meters per second. So your answer is going to be in meters, and it doesn't even say, it just says calculate the wavelength of the light. If all your answers are in nanometers, then you're going to have to take your answer in meters and change it to nanometers. Everybody see how we set that one up?
Yes.
Yes.
Oh, let's do one more. And we'll take a break. Again, these problems are pretty similar to ones that are on the test, so if you understand them, it'll help you. Let's take a look at one more here on how to set it up. Now it was the chemist or physicist de Broglie that determined that, well, he reasoned that if electromagnetic radiation has both particle properties and wave properties, maybe matter also has wave properties and particle properties. And this is the concept, he came up with the equation for it. It's the de Broglie wavelength. And the de Broglie wavelength, you have an example problem in the chapter. I don't remember if it involves a tennis ball, but if you have things that have large mass, their de Broglie wavelength is so small that there's no equipment that could possibly measure it. So again, it's really more of a quantum mechanical thing. The de Broglie wavelength only makes sense for the smallest particles like of matter, like protons and electrons and stuff. And also is measurable.